So welcome back to the next session of the Swayam course. As a recap, in the last section, we discussed various semantic maps. I did not tell you about something called semantic integration, but we did talk about concept maps, mind maps, and I told you that they are called semantic maps. Semantic in this particular case means words. And they are semantic maps because very often students think in terms of words, but putting it together in a visual representation actually enables them to understand better. We also looked at essentially a case wherein there was inquiry-based learning that was enabled. So we asked questions, as you might have seen, and this is very important. The kind of questions that you ask should be connected with the learning that you want your students to have. And that is really where the experience of the teacher becomes very important and the insights of the teacher becomes very essential. So the kind and quality of questions we ask is very critical because that's really what guides the students and hence creates a certain mental landscape for her or him. Semantic integration is a very important idea as well and something I want to introduce you to today. And it is the idea that students always have some background, some context when they actually come into our classes. And it is important for us to actually ensure that the experience they have had so far, the learnings they have had so far is connected with the learning that they are having in our classroom setting. It is through that integration that they can see value and meaning and perhaps also feel motivated to be part of the class. So this is very essential. And again, semantic maps can help in this kind of semantic integration. In the last class, in addition to inquiry-based learning, we talked about inclusive education. I hope you take it very seriously. And all educational institutions have a long way to go before they become truly inclusive in their philosophy, their practice, their approach, and in their day-to-day functioning. So today, what we will be discussing as far as the contents are concerned would be the following, something called the radius ratio rules. And we will arrive at this again by using the inquiry-based learning approach. We will get students to look up independently at something called interstitial sites, and then we will end the discussion using a few questions and perhaps even a few insights about the phenomena of diffusion. So the first one is radius ratio rules, and the question that is meant to promote this inquiry is the following. Okay, so let's look at the question here. So give an example of a material that has both cation and anions. This should be, I hope, somewhat straightforward given the discussion we have had in the last class. And geometrically speaking, now we are going to map this to a geometry problem. Okay, geometrically speaking, can you arrange the cation and anions together? Can you arrange it together? If so, how would you arrange it? That's one question. And you should arrange it to render them stable. So whatever arrangement you propose, think about whether or not it's likely to be stable. Number one. Now, number two, do you think you need to play with either the coordination number, okay, or the radii of the participating ions in order to render stability? So you have drawn some structure. You think that it's not stable. So modify it so that it becomes stable. When you modify it, give the rationale behind the modification. So do you understand? So first is one material where there are both cations as well as anions. Draw it as you think or deem fit. Between the two of you, you can discuss the stability of it. Is it reasonable, unreasonable, what is happening? And through these discussions, come up with a stable structure. If it is not stable yet, you can debate with one another about whether you have to play with coordination number or the sizes of these cations and anions. It's up to you. You understand? Okay, please. So you can look at something called Ionic Radii if you just so that you become a little bit more comfortable when you're drawing these ions, because you might want to draw ions using spheres, right? Some spheres like this. So what these sizes would be, etc., would make sense provided you know the radius, right? So this is not a very good sphere, but let me say that I have one sphere and another sphere, and I'm going to put a bunch of these spheres around one another. Which one corresponds to cation and which one corresponds to anion is not clear to me right now. But if you know the ionic radii, it would be clear. So why don't you look at ionic radii? So ionic radius. So if you choose, let us say, silver chloride or sodium chloride, then look at the ionic radius of sodium, look at the ionic radius of chloride, and then make things by and large to scale if possible. So chloride 1.75 angstrom, sodium 1.02. So which one is smaller? Sodium. Do you want to put a charge on that? Yes. So sodium is plus yours, right? Cl is minus. Very good. So the charge has to be put on top. It should be the superscript. So Na plus Cl minus. So there are some sizes. So this is about 1 angstrom. So now why don't you start putting chlorine atoms and sodium atoms together? Because in a real solvent you don't have just one sodium and one chlorine, right? You have multiple sodiums and multiple chlorides. So why don't you put it together? Let us see how it comes. If you wish, you can have a two-dimensional representation. Let's see what happens. Yeah, so you can choose a plane. Fine. So in 2 dimensions, see.
Sodium chloride.
Fine. No, forget that. My question is, can you think about ways in which they can come together? Okay. In a stable manner. Does their coordination matter? If yes, why? If not, why? Do their radii matter? If yes, why? If not, why? That's the question. You understand? So instead of Na plus, if I make potassium, will the story change? Instead of that, if I make it cesium, will the story change? How will the story change? Clearly the packing will change. So you can see that immediately the crystal structure will change. So if I play with the cation radius, if I keep the anion constant and I keep increasing the cation radius, then you can see that there will definitely be a change in the kind of coordination between the cation and anion. That is somewhat clear, isn't it? That is what you are able to see. Very good. Fantastic. So you can also try to play with the sizes. Yeah, that's what you are trying to do. Very good. Play with the sizes. It's an interesting question, isn't it? Because which one is your anion and which one is your cation?
One is sodium is cation.
Okay.
And the bigger one is chloride ion. And one is A below and one is above also chloride ion.
So do you think that these would have to be perfectly similar to one another? Like here, for example, there is a huge gap between the two. Is that likely in nature?
Yeah.
It just happens.
Yeah.
Okay, fine.
So while drawing, some gaps are appearing.
Fine.
So in actual practice, all of them might touch each other. If we draw a clock.
Yeah, keep going. So, but what will happen in these? Very good. So, see, chlorine, very good. So, you are touching upon something important. Suppose I make the sodium ions very small, right? Then it would draw the chloride ions inwards. I am not saying that there is a situation with sodium, but let me say that the cation in between I make it smaller and smaller and smaller and smaller and smaller and smaller. Then what would happen? All these anions are being drawn in closer to one another, but they are all negatively charged. So that would result in a very unstable structure, isn't it? Correct? Do you see that? So if I take this, I make it very small, then all the negatively charged particles would be drawn close to one another, and that would result in a very high energy structure. That would be an unstable structure. So do you think the ratio of the radii, okay, so in this particular case, the anion radius to the anion radius matters. It matters. It matters so much. It matters so much that if you actually have R plus by R minus that is extremely small, the crystal wouldn't even exist. There would not. So there is a limit to the R plus by R minus, below which stability is not possible. That is called the critical radius ratio. and this is a purely geometrical result. You can show that this R plus by R minus, when it is 0.155, this is where the stability window starts. So it has to be more than 0.155. So if it is not, then clearly what happens is the anions get drawn close to one another, and it's a bad situation. All the anions would touch one another, and that would be clearly a bad situation. Okay. So what you have begun to appreciate, I think, as a consequence is that clearly the R plus by R minus matters. It matters to the stability of the crystal. Does it matter to the structure of the crystal?
Yes.
Obviously. And hence you can in principle come up with a table like this. It is called the radius ratio. So you can see here, for instance, if the cation is very small, then it's unstable because they are all touching one another. Here they are all touching one another, but they are also touching the cation. So that is rendering it somewhat stable. But if they are not touching one another and they are only touching the oppositely charged ion directly, they are relatively alright. You understand? So this would be a stable structure, this would be the limit of the stability, and this would be an unstable structure. Okay? And on Wiki, there is a very nice article on radius ratio rule. So let me just pull that out. So this is the table that you will see, which is there in many textbooks. In fact, it has a long history. It has been around for a while, and remarkably, the argument is purely geometric. So this is and it comes from Wiki. I have cited Wiki here. So less than 0.155, you cannot expect stability. All right. In 3 dimensions, so it basically becomes a linear system. In 3 dimensions, it's not possible, but I could have one sitting next to another. That is allowed. So that is why it's considered to be a linear system. It won't be a 3-dimensional system. Here, it becomes a 2-dimensional system, triangular planar. But beyond that, it immediately enters into the 3-dimensional regime. So beyond this R plus by R minus, 0.225 and beyond, you can anticipate 0.225 to 1, you can anticipate it to result in an extended solid. Less than 0.155, you expect it to be a linear system. It would be a 1-dimensional system, most likely a molecular system. You understand? Beyond 225 and below 1, you can expect it to be an extended 3-dimensional solid. You understand? So these are called radius ratio. That was one of the things I wanted to cover. Another thing is, take a look at Google Images and search for this keyword, interstitial sites. Interstitial sites. What are the kind of images you see for interstitial sites? Huh? Oh, okay. So tetrahedral and octahedral sites. Can you go to the board and draw it for me, please? You are welcome to take your cell phone with you.
Similar things, sir.
What are
Popular diagrams for octahedral words.
Okay. So what are interstitials? What do they mean? Can you look at the dictionary definition of the word interstitial? You can just open it in a new tab. What is this? Can you explain to me what
So,
you found in your images?
Tetrahedral site is like you consider a plane, a bottom plane which has 3 atoms,
sitting in a
So
triangular
can you
shape.
draw a unit cell, for example, and show it to me?
Dictionary definition is
What is the dictionary definition of interstitial?
dictionary definition is an intervening space, especially a very small one.
Small part of it, big one. Small part.
So the
It's a dictionary definition. Just the dictionary definition of the word interstitial.
an intervening space.
Intervening space. So you have these atoms that are actually sitting together. There are spaces in between. Those are interstitial spaces, right? But now let us look at the volume associated with these interstitial spaces, whether they can be used for something useful. That's a reasonable question to ask. Right? So I have these interstitial spaces that are available in these extended solids. How can I use it for an engineering purpose? That's a reasonable question to ask. Right? So okay, so what kind of unit cell is this?
FCC.
So you call it a FCC, so maybe you can write down what FCC means. Very good. Now, please show some interstitial sites to me. So interstitial sites by definition are intervening sites, as you pointed out. That means they should be bounded by atoms in this particular case. So if I am looking for spaces between atoms, it has to be bound by atoms somewhere, correct?
Yes.
So let me just, so why don't you identify one space?
This center of the unit cell will be an
Center
interstitial
of the
space.
unit cell will be okay. So what kind of, can you just draw the bounding atoms, if you will, of that interstitial space? Because if it's an interstitial space, there should be some atoms sitting around it. Ah, wonderful. So what kind of space is that looking like?
octahedral site.
So, right, because it has 8 sides. Do you see that? Do you see the drawing there? It has 8 sides. So that void at the center, he claims is octahedral. That's reasonable because that's basically the geometry that is defined here, defined by the bounding atoms. So, fantastic. Very nice. So, can you identify some more octahedral sites? Is it allowed or disallowed? Okay. So, I don't see why that's an octahedral site. Can you explain to me why that's an octahedral
So you
site?
consider the next repeating unit cell. You will have a face-centered atom here. Then you will have
Yeah.
one more above
So
cell.
maybe
you will
there's
have an
another
atom
way to
here.
visualize this also. So if I take this atom here, do you see there is this line? Connect. So this atom is sitting between atom in this face center and atom behind us, right? So if I, and this is a perfectly similar situation here, correct? It's a perfectly similar situation. So how many such octahedral voids would then be there if what you said is right?
Here it will be 4 per unit cell.
Why do you say it is 4 per unit cell?
Because if you consider this octahedral site, it is shared between 2 unit cells.
Okay.
So you take
So is it going to be shared between 2 unit cells?
4 units.
Sorry, 4 unit cells. So you will have 12 edges.
Okay.
So in each edge you will have one octahedral site.
Yes.
So you will be like 12 by 4. You will get 3,
Okay.
and the center is shared by only 1 unit cell. So 3 plus 1 4.
4. So he claims there are 4 octahedral voids in that particular structure. How many of you are convinced? You're convinced. You're convinced. You're not convinced. So you need to advocate your position a little bit more. So he says the octahedral void in the center of that unit cell, that sits in the unit cell, isn't it? So you count it as 1. Okay. Then he says, then there's another octahedral void there. Do you see that? Along that edge. But that edge is shared by 4 unit cells. So you shouldn't count it as a single octahedral void. You should count it as single divided by 4. So there are how many such octahedral voids? How many such octahedral voids exist?
The one in that edge.
Okay.
One octahedral side per edge.
Okay. So how many edges are there?
12 edges are there.
12 edges are there. So how many octahedral voids should be there? 12 divided by 4. So how much is that? 3.
Yes.
Then there is 1 at the center. So 3 plus 1, 4. Is that clear? Is that clear? Okay. Is that the only kind of void that you find?
Tetrahedral void we have.
What is tetrahedral void? No, maybe you can erase this. We have looked at octahedral void now. You can show that itself. Alright, fine. So it's not clear to me. Can you explain to me, please?
So you have this corner atom.
Uh-huh.
You have 2 face-centered atoms and one more corner atom sitting there.
Okay.
So between these 4 atoms, you just consider this between these 2 atoms. Consider a diagonal.
Between these 2 atoms?
This
Do you want
corner
to draw
atom-
a different diagram?
So for now we will omit this face atom.
Okay.
So this face-centered atom, it's there. You just consider that. So you have the bottom face-centered atom, the left side face-centered atom, and this corner atom and this corner atom. So between these 4 atoms, there will be a diagonal going this way, that direction. So you have a side between these 4 atoms, which is tetrahedral.
So do you all see that it is a tetrahedral site? Why is it a tetrahedral site? You see it, right? There are 4 faces. Very good. Fantastic. So how many such tetrahedral sites exist here?
8.
How can you be sure?
So since I said this will be on the direction of a diagonal, so you can think this one and one more from this diagonal constitutes 2 tetrahedral sites. So you can construct 4 diagonals that in a cube. So you will have 8.
Very good. So how many tetrahedral sites did you say?
8.
So please write that down. So there are 8 tetrahedral sites. And how many octahedral sites were there? 4. So you can write that also down. So there are 4 octahedral sites. Wonderful. Very nice. So these are places where you can position additional atoms, isn't it? These are places that are available. As he pointed out, these are intervening spaces where you can position additional atoms so that they get bonded to these other atoms, either tetrahedrally or octahedrally. That's the argument. Is it clear? Now, given that he says this, why don't you now discuss between octahedral and tetrahedral sites that he has pointed out. Let's call them voids for the time being. Okay, how many of you know the meaning of the word void? Void simply means empty space. Okay, so I have some tetrahedral void where I can place an atom, I can thrust an atom. I have some octahedral voids where I can place an atom, I can thrust an atom. Okay, so suppose I have a big atom and I have a small atom. Where is it likely to go? So another way of asking this question is, do you think that there is more space in the octahedral void, or do you have more space in the tetrahedral void? Which one is a bigger void? Why don't you discuss with one another? Draw and see.
I think it depends upon crystal structure.
Okay.
Or FCC operator will be there.
That is right. So clearly you could see that, right? The way he has drawn it, the octahedral is a bigger void. Okay, the octahedral is a bigger void, the way he has drawn it. So if you have a big enough atom, it would rather go there, to the octahedral site. It would sit between those, it would sit along at the center of those edges, right? But if it's a very small atom, it is possible that it actually goes to the tetrahedral void. It's possible in this particular crystal structure. Is it clear? Right? It's clear, correct? Very good. Now we are going to actually do a very interesting thing, and remarkably, this thing that we are going to do is very similar to stuff that you have seen in your day-to-day life. You open a perfume bottle, the perfume eventually, and goes to all ends of the room, right? And it is because of some phenomena called diffusion. It's a random walk. These perfume molecules are like drunkards. They just go all over. And in general, when you open the perfume bottle, there is a very high concentration of perfume molecules here. So they eventually go down. They go away to places where the perfume molecules are not there. So there is, in general, a certain direction from a region of high concentration to a region of low concentration. So this phenomena, it's a random walk kind of an event. Okay, it's called diffusion. It's called diffusion. Now what we are going to do is, I'm going to ask a few questions about diffusion, and you can again use your devices to think about this. So the first question that I am going to ask about this is the following. So would diffusion depend upon the temperature of a structure? So now instead of allowing perfume molecule to go through the room, I am basically going to have some atoms sitting here, and I want those atoms to go through this particular lattice. So I am going to change the situation. Instead of allowing the perfume molecules to go from the region where the bottle is opened to the regions where bottle has not been opened, to regions far, far away from the bottle, I am basically going to introduce some atoms. I have some atomic flux. I am going to shower atoms from some direction, and I am allowing them through this particular lattice. Okay, so do you think that the atomic motion through the lattice will depend upon the structure? Number one. Number two, what I am going to do is I am going to freeze this lattice. I am going to lower the temperature, lower it. Will this diffusion continue? Those are the two questions I want you to discuss. First is, does the structure matter? Number two, what will happen if I lower the temperature? Maybe to 0 Kelvin. Okay, so please discuss this with one another. You understand the question? You understand the question? So, I told you about diffusion. So, diffusion, the analogy that I made here for the purpose of thinking about this problem is, suppose I open a perfume bottle. You know that immediately the perfume molecules would go to all the corners of the room. Okay, it would go. And these perfume molecules, it is not that they are directed in a particular direction. No, they are going in all kinds of directions. So they are like a drunkard. They are moving in all possible directions. But in general, they will have a flux in this direction because of the fact that here is where you have a very high concentration of molecules, and they are all going all over. Some of them might also be coming back, but in general, there is a flux outward, away from the source. You understand? Now I am going to do a somewhat analogous experiment, but instead of perfume, I am going to make some atoms incident on this particular lattice. I am going to shower some atoms onto this particular lattice. You understand? So now these atoms have to walk through this lattice. Okay. So does the structure of this lattice matter?
Yes.
If I change this to some other structure, will it actually, the atoms go through it in the same manner? That's the question number one. Number two, I am going to freeze this. Okay. What will happen to this particular process of diffusion through the lattice? That's the question. So please discuss with one another. You understand the question now? Please. Please proceed. Yeah. So you can draw a diagram if you want. You can say atom will go here first, then here first, here next, and so on, so on. You can do all that. You understand? So I am using an atomic beam, if you want to think of it as an atomic flux. I have a lattice, and it's incident on that particular lattice. What's going on?
It will depend
Obviously. So it is very clear that diffusion will be very dependent on the structure. Right? If the structure is very open, diffusion is likely to be faster. Right? If it has lots of voids, diffusion will be faster. Correct? If it has lot of regions wherein, let us say, atoms, an atom here is missing, an atom there is missing. So clearly diffusion would be encouraged. Correct? So diffusion would be encouraged by the presence of what are called as vacancies. That means absences of atoms, and by the presence of open structures. So if you have a structure with lots of voids, lot of intervening spaces, diffusion would be encouraged. A relatively open space, diffusion can happen. But what would happen if I freeze the temperature? If I lower the temperature to, let's say, 0 Kelvin, will any diffusion happen? Obviously not, because they need some energy to walk through the lattice. They don't have any energy to walk through the lattice. Correct? So at perfectly 0 Kelvin, diffusion goes to 0. Alright, in your sheet, draw how atom could hop from one interstitial site to another or one vacant site to another. Consider a two-dimensional lattice. You don't even have to show it in 3 dimensions. Two-dimensional image. You have some foreign atom. You have a lattice. You have a lattice that is very real. That means there could be some vacancies. There could be some interstitials. There could be combination of vacancies and interstitials. All of these possibilities exist. So where are your interstitials? Can you show me interstitials in this lattice that you have drawn? This is correct. That is correct. Can you show me the interstitials?
So these portions.
Yeah, correct. So those are available, no, for diffusion. Correct. Very good. So it could go here, then from here to here, here to here, here to here. All of these possibilities. Why don't you? And there's a vacancy here. So once it comes here, it could also go here. Right? So it could come here. Right? Now let us say that I don't have any foreign atoms. So I have this lattice. I have a vacancy here. This atom could come here, and this vacancy essentially moves here. Correct? So vacancies could also diffuse as a concept. So atomic diffusion and vacancy diffusion are actually similar. Right? They're related in your picture. Did you understand? So for example, if I have vacancy here and I have no foreign atoms, let us say, this atom would come here, then you have a vacancy, and this atom would come here, then you have a vacancy. So vacancy could actually move rather rapidly. Correct? Do you understand? And then if you have these interstitial positions, then the atom would go from this interstitial position to the next to the next. Do you think bonding will influence the diffusion?
Yes.
Absolutely. So if you have an atom that is very strong, let's say it's an interstitial atom, but it's very strongly bonded to all its neighbors, then it won't move. Correct? So bonding also plays a very important role in diffusion. No question about it. So is this diffusion a little bit like reaction rate? Yeah, because you have this state and this state goes to some other state, right? So there is, so very similar to chemical reactions which have a rate. Diffusion is also about a rate. It's about a movement. Okay, and just like in chemical reaction rates, you can write down the Arrhenius equation, which is that the rate R is proportional to activation barrier divided by RT. In perfect analogy, you can write diffusion is proportional to exponential of minus E activation. This is for diffusion divided by RT. Now, the way you showed it, there are different types of diffusions possible. No, there could be through the interfaces, interstices. It could be through vacancies. All these possibilities exist. All right. So, do you think that each of these possibilities will have a different activation barrier?
Yes.
Obviously. So if you have multiple mechanisms, you will actually have multiple diffusion pathways, and each one of that will have its own unique activation. Natural. It's pretty natural. Very good. So why don't you spend some time looking for diffusion data? Okay, the diffusion coefficient of some ion in water, diffusion coefficient of some ion in silica, diffusion of some ion in metal. Just take a look at it, or atom in a metal. So let us make a table of diffusion coefficients. So we'll take some examples. And remember, diffusion will depend upon temperature. We discussed that. So when you give me the diffusion coefficients, it should be at a certain temperature. So diffusion at a certain temperature. So that's why I've written system. So the atom that you're interested in, the lattice in which the diffusion is happening, and the temperature. You'll have to tell me all three details. Some data will come out. Yeah. Okay. Please tell me. So CO2 in air, what is that?
16 millimeters square per second.
16 millimeters square. So that is 16 into 10 to the power of minus 6. What's the unit?
Millimeters square per second.
So that is meter square per second. So this is correct. So most gas molecules are moving about in about 10 to the power of minus 6 meter square per second. Okay. Actually, so this is right. Yes.
Then that is in water is
Okay.
0.0016 millimeters square per second.
Wow. See, look at the difference. So the diffusion in air versus diffusion in water. How different are they? 10,000 times different. That's about right. 10,000 times different.
Yeah.
Did you notice that? Now let us look at one more data point. So let us say carbon in iron. But in this particular case, you will have to mention the temperature. So this is at room temperature. This is also at room temperature.
We have some data for diffusion of inorganic cations in water.
Okay, you want me to write that down? I can do that. Yes. It will also be comparable. Yeah, tell me.
So for calcium plus 2,
Ca2 plus aqueous in water, yes.
it is 0.793 into 10 to the power minus 9 meters square per second.
Now this is interesting. You see, carbon dioxide is moving much faster, isn't it? So this is 1.6 into 10 to the power of minus 9. Actually, it's carbon dioxide is moving slower, because if you convert this, so you would have 1.6 into 10 to the power of minus 9, and this 0.793 into 10 to the power of minus 9. Okay.
So it is moving faster than
Carbon dioxide is moving faster, and there may be a good reason for that, because you see, this is an ion, so it gets solvated by water, but this one is neutral, so it makes sense. So anything that is solvated would actually move slower naturally.
See, even carbon dioxide might form that H2CO3 in
But you see, carbon dioxide looks like this.
This is a molecule and this is a cation also smaller size.
And not only that, this is a linear molecule, so with perfectly zero dipole. So you are right, it has sparing solubility, very, very sparing solubility. Yeah. Next. So one more data, please. This is from solids. I want something from solids, from polymers, from glasses.
What is anion?
Solids. So
We'll have a data for carbon in alpha.
okay, very good. Carbon in alpha ion, yes.
So it says that minus 35 degrees Celsius. So
Okay.
it will be around 10 power minus 20 centimeters square per second.
10 to the power of minus
20
unit.
centimeters square per second.
So convert that to meter square.
10 power minus 4.
No, 24. Correct?
10 power not.
So this is at minus 35 degrees Celsius. Convert that to Kelvin, please. How will you convert degree Celsius to Kelvin? Add 273.
238.
Correct.
At 200 degrees Celsius,
Very good.
10 power minus
10
10.
to the power of?
Minus 10.
Yes. Did you see how dramatically different it is? So you see 10 to the power of minus 24. 273 is 200 degrees Celsius is basically 473 Kelvin, right, in absolute scale. So you have increased this temperature by twice, but look at it. You have improved the diffusion coefficient by 14 orders of magnitude. Did you see that? And by the time you take it to melting point, it would reach 10 to the power of minus 6. Very easily, very readily. You understand? Did you see this? So these are about right. These are the kind of diffusion coefficients you expect. So take a look at least one data for polymers.
So diffusion coefficient of species in polymer
Some
medium.
species in you mentioned the species and polymer. What is the diffusion coefficient? So do you expect diffusion to happen in polymers also?
Yes.
Obviously. Do you expect diffusion to happen in glasses?
Yes.
Absolutely. So let us say I have glass and I have a crystalline form of exactly the same material. So composition is the same, which is silica. I have silica glass and silica quartz. Which one will have higher diffusion coefficient?
Crystal. I think glass.
Glass. Why? There are a
Glass
lot
will
of
be-
spaces, a lot of open spaces, right? So typically glasses tend to have much higher diffusion coefficient than the corresponding crystalline system.
So glasses will have more. The spaces are more ordered in a crystalline medium, right?
That is true. So that is why this is, as I told you, there are cases wherein this is not the case. So there are cases wherein glasses are extremely impermeable. Okay, but most of the examples actually would be such that glasses allow greater permeation.
I think if the glass doesn't contain more network formers, it will be diffusion coefficient will be high.
Right. But glasses inevitably have some network forms.
But in some classes, the network will be very complex.
That's right, and that could actually affect the diffusion coefficient. That's his point. That's true. That's right. So it's also very temperature dependent. So you could actually have some temperature regimes where that's not the case. Where diffusion coefficient of the in glass might actually be slightly higher than that of the corresponding crystal. So it's possible or lower. So it's very temperature sensitive, especially for ceramics. Very temperature sensitive. But look at this. This is also very dramatic, isn't it? This is not a ceramic, and still you see 10 to the power of minus 24 meters square per second goes to 10 to the power of minus 10 meters square per second over 200 Kelvin essentially. Alright. Yeah, what data did you find for polymers?
Diffusion coefficient of oxygen in polyethylene at different temperatures.
Yeah, please tell me.
At 263 Kelvin, it's around 0.8 10 power minus 10 meters square.
10 to the power of minus 10. So that is for 200 Kelvin.
263.
263 Kelvin. So that is comparable to this, isn't it? Comparable to this, but what's the value that you found?
10 power minus 10.
So you see, so it's very porous. Like polymer networks are very porous. Did you see that? So diffusion coefficient in the polymer is comparable to the diffusion coefficient in this alpha iron, but at 200 degrees Celsius. So at close to 0 degrees Celsius, you have permeation through polymer that is comparable to the permeation through alpha iron at hundreds of degrees Celsius. Got it? So which polymer is this?
Polyethylene PEC.
So this is polyethylene, and the diffusion coefficient of oxygen gas at what temperature?
263.
So this is polyethylene, oxygen, 263 Kelvin, huh?
Yes.
So that is fairly low. It's lower than 0 degrees Celsius, and you have 10 to the power of minus 10 meters square per second. So this is really interesting, isn't it? Very interesting. So polymers are highly diffusive. Highly diffusive. Right? So without heating it up much, you can get extraordinary diffusion, extraordinary permeation through polymers. Right? Very good. So now here is an interesting question, and with this we will end. can the idea of diffusion be extended to charged particles in a solid? Suppose I have a solid. Yeah, I have a solid. I am going to inject some electrons here. Can I think of those electrons as moving inside the solid the way in which perfume is moving inside this room?
Yes.
Perfect. Why not? Absolutely. Because if I am injecting into this particular solid, there is a concentration gradient and it would actually move. This is very important for semiconductor devices. You inject electrons and they actually have to move. It's not just a combination of the movement under the electric field, but also the movement because of diffusion. That has to be taken into account while describing the device operation. In, let us say, PN junction devices, PN junction diodes, solar cells, and so on.
Ultimate cause is electric field only, because at one end if there are a lot of electrons, then they are experiencing heavy repulsion from each other. So that is why they would diffuse to reduce.
So you will have to delineate it into two reasons. One is because of the fact that there is higher concentration. So if you write out an expression only because of concentration gradient, that is diffusive. You can write out an additional drift, and that will actually take into account the electric field. So you are right. How would you actually inject electrons into it? By applying the electric field. So these electrons are moving up in a direction based on the electric field that you are applying. Number one. So that is called drift. But independent of that, based on the discussion we had in this class, I inject electrons, they have a concentration. Here they would go down to concentration gradient. So you have to add the two terms. That is when you can actually capture the total movement of current in this particular system. That's the whole idea. Okay, wonderful. And this is very important for describing semiconductors, behavior of semiconductors under electric fields, and so on and so on. Now think about this question also. And this is a homework question. I take an atom, I put it inside a semiconductor, I put it inside, let us say it is in an interstitial position, or it is substituting another atom. So let me say that I am taking boron, I have diffusively doped boron inside silicon. You understand? So we now saw how diffusive doping is possible. I have the lattice, I expose it to boron atoms from one side, eventually these drunken boron atoms will go into the lattice. Okay. Alright, and if they have sufficiently, based on their size, they could either occupy a vacancy that might be there, and in which case it would be substitutional doping, or it could go into these interstitial sites and so on. For the sake of this argument, let us say that I have boron and it is actually going, it's knocking out a silicon atom, or it's occupying a silicon vacancy, one of the two. Alright, so now the question is, can I, in a targeted manner, get this boron in this semiconductor to be preferentially ionized? So I want to ionize that boron. Is it allowed, disallowed? Totally allowed. That boron is bonded to silicon in the vicinity. There are some orbitals about them. You provide the energy corresponding to the electronic excitation that is required for ionizing that particular boron. It's allowed. And in fact, this is the principle behind doping. So very often doping is done diffusively. When you do diffusive doping, you end up having an atom in this particular post lattice, and if you can provide energy for this ionization to happen, lo and behold, there is doping. And that's the principle behind NNP type doping in the diode. Okay. Typically, this ionization event would be such that at room temperature it can happen. The thermal bath that we are sitting in is sufficient for that ionization to happen. And that is why the transistor device around you, you don't have to constantly give energy. Then, at room temperature, in this particular environment, they naturally end up having these events that are responsible for the release of electrons or holes and so on, necessary for the device operation. Okay, and does it matter where it sits? Does it matter? Absolutely. Whether it sits in interstitial, because the kind of bonding would be different. Whether it sits in the octahedral site or the tetrahedral site or the interstitial site, does it matter? As far as bonding is concerned, absolutely. It does matter. Okay. So with that, we'll summarize. So as far as the recap is concerned for pedagogy, we discussed semantic maps and semantic integration. That was the concept that we introduced. And we also have been, by and large, discussing the theme of inclusive education. And We have been using something called inquiry-based learning here, wherein I have been asking targeted questions to get students to think in a very specific manner. In the last class, they also got to make concept maps. They can in fact do that even for today's session. They have also used data that is available to them to come up with meaningful numbers to inform their learning, to inform their concept maps in their own minds, and so on and so on. And they were also able to visualize interstitial positions, voids that can exist in lattice, and they were able to also rationalize where the radius ratio rules come from and be able to develop a physical picture, a physically reasonable picture of diffusion. So with that, we come to the end of this SWAYAM session. Thank you very much.